Welcome! In this session, we'll explore LeetCode problem number 1210, minimum moves to reach target with rotations. This is a fascinating problem that involves navigating a two-cell snake across a grid while considering both rotations and movements. We'll break it down step by step and analyze the most efficient approach to solve it. Let's dive in. In this problem, you're given an nxn binary grid where each cell is either empty, represented by 0, or contains an obstacle, represented by 1. The task is to navigate a two-cell horizontal snake from the top left corner of the grid to the bottom right corner. The snake starts with its head at grid 0, 0, and its tail at grid 0, 1. The goal is to move the snake so that its head ends at grid n1, n1, and its tail occupies the cell directly to the left at grid n1, n2. To achieve this, you have 4 possible moves. You can shift the snake one cell to the right, one cell downward, rotate it clockwise around its tail, or rotate it counterclockwise around its head. Each of these moves has to be valid, meaning the snake must remain within the grid and avoid overlapping with any obstacles. The goal is to determine the minimum number of moves required to reach the target position. If it is not possible to reach the target due to obstacles or other constraints, the function should return -1. Let's explore an example to make this clearer. Consider a grid where the snake starts at the top left corner. The snake must navigate through empty cells and around obstacles to reach the bottom right corner. The output in this situation would be the least number of valid moves, or -1 if the target cannot be reached. For example, in a grid with dimensions 6x6, the minimum number of moves required to reach the target position might be 11, depending on the placement of obstacles. In the first example, the snake starts horizontally at the top left corner, spanning grid 0, 0, and grid 0, 1. The goal is to move it to the bottom right corner, where it will span grid 5, 4, and grid 5, 5. The minimum number of moves required in this case is 11. The obstacles in the grid require the snake to navigate carefully, potentially rotating and shifting multiple times to avoid collisions. However, in some cases, reaching the target may be impossible. For instance, if the grid has obstacles blocking all possible paths to the bottom right corner, the function will return -1, as shown in another example. Here, the snake cannot navigate through the obstacles to reach the target position. The constraints and edge cases for this problem provide additional context. The grid size can range from 2x2 to 100x100. And the snake's initial position is always valid and free of obstacles. The snake must remain entirely within the grid at all times and cannot move onto or through obstacles. Edge cases to consider include grids with no obstacles, where the solution is straightforward, and grids where the bottom right corner is blocked, making the goal unattainable. Additionally, the snake may need to rotate multiple times to navigate tight spaces or obstacles, and the solution must account for both small and large grids efficiently. Handling these scenarios correctly is essential to solving the problem within the given constraints. To solve this problem, we need to guide a two-cell horizontal snake from the top left corner to the bottom right corner of a binary grid while navigating obstacles and performing rotations as needed. To begin, we consider 2 primary approaches. The first, a brute force approach, involves simulating every possible move up, down, left, right, and rotation for the snake recursively until it reaches the target. While this method is conceptually straightforward, it has significant drawbacks. Specifically, it's computationally expensive because it explores all paths indiscriminately, including invalid or redundant ones, leading to an exponential time complexity. For larger grids, this makes the brute force approach infeasible. On the other hand, we also considered a breadth-first search, or BFS, approach. Treating the problem as a shortest path search, BFS represents each state of the snake, its position and orientation, as a vertex in an implicit graph. By exploring all valid moves level by level, BFS ensures the shortest path to the target is identified. Key steps include maintaining a queue to track the snake's state, validating potential moves, avoiding obstacles and boundaries, and using a visited set to avoid revisiting states. The process terminates once the target position is reached with the snake in a horizontal orientation. The BFS approach has a time complexity of n squared, where n represents the grid size. This is because each state in the grid is processed only once, and there are at most n squared states to consider. The primary advantage of BFS is its optimality for shortest path problems, guaranteeing that the minimum number of moves is found. Additionally, it is relatively simple to implement and does not require complex heuristics. Another approach we considered was a asterisk search, which builds upon BFS by using a heuristic function to prioritize states that appear closer to the target. While this can reduce the number of states explored, the effectiveness of a asterisk heavily depends on the quality of the heuristic. For example, a Manhattan distance heuristic might provide a rough estimate of the remaining distance, but it doesn't fully account for the snake's orientation or the need for rotations. Moreover, maintaining the priority queue required for a asterisk adds additional overhead, and for smaller grids, the performance gains compared to BFS are often negligible. This makes a asterisk less favorable in the context of this problem. Among the approaches considered, we ultimately chose breadth-first search as the most suitable strategy. BFS stands out for its simplicity, as it is easy to implement and guarantees correctness by always finding the shortest path in an unweighted graph like our grid. This makes it an ideal choice for a problem where the goal is to minimize the number of moves. Its efficiency is another key factor. While a asterisk could marginally reduce the number of states explored, the grid size is small enough that BFS runs comfortably within time limits. In contrast, the brute force approach is computationally prohibitive, and a asterisk introduces unnecessary complexity without significant performance benefits for this problem. BFS strikes the perfect balance between simplicity and efficiency, making it the optimal choice. By focusing on straightforward state exploration and leveraging a visited set to prevent redundant calculations, BFS ensures both correctness and performance. There are several key observations that simplify solving this problem and highlight the strengths of the BFS approach. First, the snake's orientation, whether it's horizontal or vertical, is critical for determining its possible moves, as this directly influences state representation and move validation. Second, obstacles and grid boundaries must be carefully handled to ensure the snake does not overlap invalid cells. Third, BFS naturally processes states in increasing order of moves due to its level order traversal, guaranteeing that the shortest path is found. Finally, using a visited set is vital, as it prevents cycles and avoids redundant calculations, which significantly enhances performance. When comparing trade-offs, the brute force method, though exhaustive, is far too slow for practical use. Asterisk, while potentially more efficient for larger grids, adds unnecessary complexity for this problem. BFS, on the other hand, strikes the perfect balance, offering simplicity, correctness, and efficiency. In conclusion, BFS is the most appropriate approach, as it ensures optimal performance and correctness without introducing additional complexity. In this problem, we're tasked with navigating a two-cell horizontal snake through a binary grid, starting from the top left corner and aiming to reach the bottom right corner. The grid consists of obstacles, represented by 1s, and open spaces, represented by 0s. The snake can move right, move down, or rotate between horizontal and vertical orientations, provided the movement is valid. The goal is to determine the minimum number of moves required to reach the target position, or return -1 if it's impossible to do so. To tackle this, we first need to represent the state of the snake. The state can be described as a tuple x, y orientation, where x, y represents the top left cell of the snake, and orientation indicates whether the snake is horizontal 0 or vertical 1. For instance, if the snake starts in a horizontal position at 0, 0, it occupies the cells 0, 0, and 0, 1. This state representation is fundamental for tracking the snake's position and orientation during the algorithm's execution. Once we have the state representation in place, the next step is setting up the structures required for our algorithm. We'll use a queue to perform breadth-first search, or BFS. The queue will initially contain the starting state 0, 0, 0, meaning the snake begins horizontally at the top left corner. To prevent revisiting the same states and creating endless loops, we'll maintain a visited set. This set will store all states the snake has already explored, represented as x, y orientation. Additionally, we initialize a move counter to track the number of moves made during the search process. As we perform BFS, we'll iterate over the queue by dequeuing the current state, x, y orientation. If this state matches the target state, n1, n2, 0, where the snake is horizontal at the bottom right corner, we can immediately return the move counter, as we've found the shortest path to the goal. To proceed with BFS, we need to generate all valid moves for the snake from its current state. First, if the snake is horizontal and the cell to its right is within bounds and open, we can move right by enqueuing the new state, x, y plus 1, 0. Similarly, if the snake is vertical and the cell below is within bounds and open, we can move down by enqueuing, x plus 1, y, 1. The snake can also rotate. For example, if the snake is horizontal and there's enough vertical space below, it can rotate clockwise to become vertical, resulting in the state, x, y, 1. If it's vertical and there's enough horizontal space to its right, it can rotate counterclockwise to become horizontal, enqueuing, x, y, 0. After generating these moves, the new state is added to the visited set to avoid revisiting it. At the same time, we increment the move counter to reflect the progress made to the next BFS level. Finally, we ensure that all boundary conditions are respected, such as avoiding obstacles and staying within the grid limits. This algorithm leverages breadth-first search because it guarantees the shortest path in an unweighted graph, which is perfect for this problem where each move has the same cost. By representing the state as x, y orientation, we can efficiently track the snake's position and orientation, ensuring that all configurations are accounted for. The visited set is crucial for preventing cycles and redundant computations, which significantly boosts the algorithm's efficiency. The queue facilitates level-order traversal, while the set ensures no state is revisited. Key operations include validating states to ensure the snake's head and tail are within bounds and not on obstacles, checking additional cells when rotating to ensure feasibility, and carefully handling edge cases like boundary conditions. In terms of complexity, the time complexity is O, n squared, where n is the grid size, as BFS explores all possible states. The space complexity is also O, n squared, due to the storage requirements of the visited set and queue. To solve the problem of finding the minimum moves to reach the target with rotations, we start by importing the DEET class from the collections module, which will help us manage our queue for the breadth-first search. Inside the solution class, we define the minimum moves method, which takes the grid as input. First, we determine the size of the grid, n, and define the possible directions the snake can move or rotate. Each direction is represented as a tuple, where the first two elements indicate the movement in the x and y directions, and the third element specifies whether the action involves a rotation. For example, 0, 1, 0 represents moving right without rotation, while 1, 1, 1 represents rotating clockwise. Next, we define two helper functions, can_move and can_rotate. The can_move function checks if the snake can move to a new position without colliding with the grid boundaries or obstacles. It considers the snake's current orientation, which can either be horizontal or vertical. Similarly, the can_rotate function ensures that a rotation can be performed by checking a 2x2 area for obstacles. These checks are essential to avoid invalid moves. Finally, we initialize a set called visited to keep track of explored states and a DEET queue to manage our BFS exploration. The queue starts with the snake's initial state at the top left corner, facing horizontally, with 0 steps taken. This setup ensures we systematically explore all possible configurations to find the shortest path. The main logic of the algorithm is implemented within a while loop that continues as long as there are states in the queue to process. At each step, we dequeue the current state, which includes the snake's position, orientation, and the number of steps taken so far. We then check if the snake has reached the target position, which is at the bottom right corner of the grid, one cell before the last column, and oriented horizontally. If this condition is met, we return the number of steps, as we have found the shortest path. For each possible direction defined earlier, we calculate the new position and orientation of the snake. If the action involves a rotation, we determine the new orientation based on the current one. We then verify if the rotation is valid using the can_rotate function and ensure the new state hasn't been visited before. If valid, we add the new state to the queue and mark it as visited. For movements, we use the can_move function to check validity and similarly update the queue and visited set. This breadth-first search approach ensures we explore all possible states systematically, prioritizing those with fewer steps. If the queue is exhausted without reaching the target, we return -1, indicating the target is unreachable. Here, we begin our Java implementation for solving the problem. First, we import the necessary utilities, like queue and set, which will be critical for our breadth-first search approach. We then define the minimum moves method, which takes a 2D grid as input. The grid represents the board where ones are obstacles, and zeros are open spaces. The variable n stores the grid size, and we define an array called directions to represent the possible moves, moving right, moving down, and rotating clockwise or counterclockwise. Next, we have an inner state class that encapsulates the current position, orientation, and number of steps taken. This is useful for managing the states as we explore different paths. We then initialize the BFS queue with the starting state, which places the snake at the top left corner, horizontally aligned, with 0 steps taken. Additionally, we use a hash set to track visited states, ensuring that we do not revisit the same state and avoid infinite loops. Now, we process the BFS queue. While the queue is not empty, we pull the current state and extract its position, orientation, and step count. We then check if the current state satisfies the goal condition, meaning the snake's head is at the bottom right corner, horizontally aligned. If so, we return the number of steps taken. If not, we iterate through each possible direction. For rotation, we determine the new orientation based on the current one. If the snake is horizontal, it becomes vertical, and vice versa. Before performing the rotation, we check if it is valid using the canRotate method and ensure the new state has not been visited. If the rotation is valid, we add the new state to the queue and mark it as visited. For regular movement, we calculate the next position based on the current direction and verify if the move is valid using the canMove method. If the move checks out and the state is unvisited, we enqueue the new state and add it to the visited set. Finally, if no valid path to the goal is found, we return -1, indicating that the target is unreachable. Moving on to the helper methods, canMove checks if the snake can move to a new position without collisions. If the snake is horizontal, we verify that both the current cell and the one to the right are within bounds and free of obstacles. Similarly, for a vertical snake, we ensure that the current cell and the one below are valid. The canRotate method determines whether a rotation is feasible. For a rotation, we need a 2x2 grid area to be obstacle-free, ensuring no part of the snake collides during the rotation. Both methods rely on bounds checking in grid cell validation to ensure safe movements and rotations. With these checks in place, the implementation ensures a robust solution to determine the minimum moves required to reach the target while handling rotations effectively. In this example, we have a simple 4x4 grid with no obstacles. The snake starts at the top left corner of the grid, represented as 0, 0, in horizontal orientation. Initially, we define the grid size n as 4 and specify the possible directions the snake can move in, moving right, moving down, rotating clockwise, and rotating counterclockwise. We use a visited set to track the states we've already explored, starting with the initial state, 0, 0, 0. A queue is initialized for our breadth-first search, BFS, algorithm, with the starting state, 0, 0, 0, 0, representing the snake's position, orientation, and steps taken so far. In the first step, we dequeue the initial state and check if the snake has reached the target position. Since the target hasn't been reached, we proceed to explore the valid moves from this state. From the initial state, the first move we try is moving the snake to the right, resulting in the state 0, 1, 0. This move is valid as the cells 0, 1, and 0, 2 are both empty. We add this new state to the queue and mark it as visited. Next, we consider moving the snake downward, but this move is invalid because it would push the snake out of bounds. Rotating the snake is also not a valid move here, as there isn't enough space for the snake to form a 2x2 square. Moving to the next step, the state 0, 1, 0, 1 is dequeued, and we again check if the target has been reached. It hasn't, so we try moving the snake further to the right, resulting in the state 0, 2, 0. This move is valid since the cells 0, 2, and 0, 3 are empty. We add this state to the queue and update the visited set. Other potential moves, such as moving down or rotating, are not valid at this stage. The BFS process continues, exploring valid moves and avoiding invalid ones, until the target position, 3, 2, 0, is reached. The total number of steps required for this example is 6. Now, let's consider a grid with obstacles. In this case, the grid has two obstacles located in the second row at positions 1, 0, and 1, 1. The initialization process remains the same as before. Starting from the state 0, 0, 0, 0, the first move we attempt is to the right, resulting in the state 0, 1, 0. This move is valid because the cells 0, 1, and 0, 2 are empty. We add this state to the queue and mark it as visited. Other moves, such as moving down or rotating, are not valid at this point because they would either collide with obstacles or lack the necessary space for rotation. From the state 0, 1, 0, 1, we again try moving the snake to the right, resulting in the state 0, 2, 0. This move is valid since the cells 0, 2, and 0, 3 are empty, so we add this state to the queue and update the visited set. Moving the snake downward is not possible due to the obstacles in the second row. The BFS algorithm continues exploring valid moves, carefully avoiding obstacles, until the target position 3, 2, 0 is reached. For this example, the snake successfully navigates around the obstacles and reaches the target in 8 steps. Finally, let's look at a scenario where reaching the target is impossible. In this grid, the snake's path is completely blocked by obstacles. The initialization is the same, and we start by dequeuing the initial state 0, 0, 0, 0. The first move we try is to the right, but it's not valid because there's an obstacle at 0, 2. Next, we consider moving downward, which is also not valid since the snake would collide with obstacles in the first column. Rotating the snake isn't an option either, as there isn't enough space. With no valid moves available, the queue becomes empty, and the algorithm concludes that the target position cannot be reached. In this case, the output is -1, indicating that no solution exists. This demonstrates how the algorithm efficiently determines when a solution is not possible. To summarize, the BFS algorithm systematically explores all valid moves and rotations while ensuring the snake stays within grid boundaries and avoids obstacles. By maintaining a visited set, the algorithm avoids revisiting previously explored states, guaranteeing that the solution is optimal. For the examples we discussed, the outputs are 6 steps for the grid with no obstacles, 8 steps for the grid with obstacles, and -1 for the grid where the target cannot be reached. To analyze the time complexity of this problem, we start by understanding the breadth-first search algorithm used to explore all possible states of the snake on the grid. A state is defined by the snake's position, its orientation either horizontal or vertical, and the number of steps taken so far. The total number of states is determined by the grid size, which is n by n, and the 2 orientations, giving us at most 2 n² distinct states. For each state, the algorithm evaluates up to 4 possible moves: moving right, moving down, rotating clockwise, or rotating counterclockwise. Checking if a move is valid involves simple operations like boundary checks and inspecting grid cells, all of which take constant time. Since BFS processes each state exactly once and each state takes 1 time to process, the overall time complexity is proportional to the number of states, which is 2 n². This simplifies the time complexity to 2 n², which is equivalent to n². Shifting focus to space complexity, we first consider the visited set, which keeps track of all explored states. Each state is stored as a tuple and requires constant space, so with a maximum of 2 n² states, the total space for the visited set is 2 n², or simply n². Next, the BFS queue, which holds states to be processed, has a worst-case size of all possible states, also 2 n², resulting in an n² space requirement. Lastly, the input grid itself occupies n² space, as it directly corresponds to the n by n grid dimensions. Additionally, there is some auxiliary space used for temporary variables and direction arrays during the computation. However, this space is negligible compared to the larger components we've discussed. Putting it all together, the primary contributors to space complexity are the visited set, the BFS queue, and the grid storage, all of which scale with n². Thus, the overall space complexity for the solution is n². Now, let's analyze the algorithm in terms of best, average, and worst-case scenarios. In the best case, the snake quickly reaches the target in the minimum number of steps, and fewer states are explored. However, BFS still guarantees that each state is processed only once, so the theoretical time complexity remains n², even if fewer states are visited in practice. In the average case, BFS explores a significant portion of the grid as it searches for the shortest path. Here again, the time complexity remains n squared. In the worst case, the grid is mostly empty, and BFS has to examine all possible states to determine the shortest path, which still results in a time complexity of n squared. Comparing this optimized BFS approach with a naive brute force method highlights the efficiency gains. A naive approach would attempt all possible moves and rotations recursively without tracking visited states. This leads to exponential growth in the number of states due to redundant computations and overlapping subproblems, resulting in a time complexity of n squared. In contrast, by using BFS along with a visited set to avoid reprocessing states, we ensure that each state is handled only once. This optimization reduces the time complexity drastically to n squared, making the BFS approach far more efficient. Finally, let's verify why the time complexity is n squared, through a closer look at the algorithm structure. The state space is bounded by 2 n squared, as there are n squared possible positions and 2 orientations for the snake. Each state is visited at most once, which ensures that the algorithm terminates efficiently. Furthermore, operations like boundary checks, grid cell validations, and move rotations are all constant time operations, or O1. The BFS algorithm also guarantees that states are explored level by level, ensuring the shortest path is found in the minimum number of steps. Combining these factors, we confirm that both the time complexity and the space complexity of the solution are n squared. Here are some common mistakes to watch out for in this problem. First, not handling rotations correctly is a frequent issue. When you try to rotate a horizontal snake to a vertical one, both cells below the horizontal segments need to be empty. Similarly, for rotating a vertical snake to a horizontal one, the cells to the right of both segments must be unobstructed. Failing to validate these conditions can lead to incorrect solutions. Next, it's important to be mindful of grid boundaries. If your snake moves or rotates out of the grid, the move is invalid, so always ensure that all parts of the snake stay within the grid dimensions. Another common error is improperly tracking visited states. You can't just use the snake's head position, you also need to include its orientation, whether it's horizontal or vertical, as part of the state. Otherwise, the algorithm might revisit the same position with a different configuration, causing inefficiency or incorrect results. Speaking of inefficiency, an unoptimized BFS can lead to time limit exceeded errors, especially on larger grids, like 100 by 100. Avoid revisiting states unnecessarily and prune paths that don't lead closer to the target. Finally, overcomplicating the solution by using methods like DFS or backtracking can cause issues, as these approaches aren't well suited for finding the shortest path. BFS, with its level-wise traversal, is the more appropriate choice here. Now, let's focus on insights that are particularly useful for interviews. A key insight is to treat the snake's position and orientation as a single state. This can be represented as a tuple, such as x, y, orientation, where the orientation is either horizontal, denoted by h, or vertical, denoted by v. The underlying pattern here is that this problem falls under the umbrella of shortest path problems, making BFS the natural choice. By using a queue, you can explore all possible moves and rotations level by level in an organized way. To optimize further, track visited states using a set, with each state defined as x, y orientation. This prevents redundant computations and keeps the algorithm efficient. Be mindful of edge cases, like very small grids, grids that are fully blocked, or scenarios where the target is unreachable. It's also helpful to recognize connections to similar problems. For instance, LeetCode 490, the maze, involves navigating obstacles with BFS. LeetCode 994, rotting oranges, requires spreading across a grid. Problems like LeetCode 847 and 1293 also deal with state transitions and grid constraints, making them great practice for this variation. Finally, let's discuss some alternative approaches and their trade-offs. While BFS is generally the best fit for this problem, you might consider depth-first search, or DFS. However, DFS tends to explore unnecessary paths and is less efficient for shortest path problems, making it more suitable for smaller grids. A more advanced technique is bidirectional BFS, where you search from both the start and the target simultaneously. This can significantly reduce the search space but adds complexity in managing states from two directions. Another option is using a asterisk, which incorporates a heuristic to prioritize promising paths. For example, you might use the Manhattan distance to the target as a heuristic. While this can improve performance, designing an effective heuristic for a problem involving rotations can be challenging. Regardless of the approach, remember the key takeaways: always validate moves and rotations against grid constraints and obstacles, stick to BFS with a clear state representation and visited set for optimal performance, and weigh the trade-offs of alternative methods carefully. BFS remains the most reliable choice for solving shortest path problems like this one. Great job! We've successfully tackled the problem by applying breadth-first search to navigate the grid and solve for the minimum moves. Key takeaways include the importance of BFS in grid-based problems and the significance of state representation. Remember, practice makes perfect, so keep challenging yourself with similar problems. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!